It's very, very small range, very tightly controlled, because your cells and tissues are really, really fussy. But now let's look at what things tend to be rather acidic and what things tend to be rather alkaline. Right? With 0 being acidic, and the larger the pH becomes, the less acidic it actually is. Right? So coffee's around a 5 or a 4, depending on how you make it and such, right? Baking soda is about a cartoon as we go further down. The numbers are increasing, and the numbers of OHs are diminishing. They're getting less and less. So they're giving you a cartoon picture that something really acidic has a lot of hydrogen ions in it. Something that's really alkaline has a lot of hydroxyls in it. There still might be one hydrogen in here. There still might be one hydroxyl. But they're greatly outnumbered. So these brackets are the symbols for concentration, or the symbol for the amount. And then we'll describe what this says in a minute. All right, let's get rid of our landmass here. So the equation is pH is equal to the concentration of hydroxyls over the concentration of hydrogen ions, or the concentration of protons. Right? It's basic math. Simple, hopefully, math. But if you struggle with math, realize this. Let me ask you guys this. If this number gets bigger, what happens to our answer? Anybody know?
Smaller.
It gets smaller, right? But let's do it this way. X, oh my God, is equal to 1 over 2. This isn't math, John. What are you doing? What's the answer? What is X? Anybody know? It's 0.5, right? Because you divide 2 into 1. But you can't, so you divide 2 into 10. So this becomes actually 5. What is X is equal to 1 over 3? What's 1/3 in decimal form? It's 0.333, right? Is this number smaller than that number? Yes, this number is smaller than this one. This is a bigger number, right? What happened to our answer? It's getting smaller. What's 1 over 4 in decimal form? 0.25. So as the denominator gets bigger, the answers get smaller. It's called an inverse relationship. You have, the bigger this number is, the smaller that number is going to be. And it matches with the picture. Lots of hydrogens, big number gives me a small pH scale. An even bigger number gives me an even smaller pH scale. Is the high pH high acidity, or is the high pH high alkalinity? You simply just write the equation out, then you'll be able to figure that out, right? The bigger this answer, the bigger this number is, the smaller the value gets for your pH. There's 12 hydrogens and 6 oxygens. I can see hydrogens and carbons in there, so I'm going to be guessing this is going to be organic. Over here, I've got sodium chloride. No carbons, no hydrogens, therefore it's inorganic. Water, no carbons, but it's got hydrogens, inorganic. Iron oxide, no carbons, no hydrogens, inorganic. What would this be, organic or inorganic? Carbon dioxide. Inorganic, no hydrogen, therefore it is inorganic substance, right? It does have a carbon, but they're not bound to hydrogens. It's a very sticky rule. You have to have carbons bound to hydrogens. Now we know carbon, from our periodic table, right, has 4 electrons in its outer shell. It wants 4 more. There's multiple ways of getting all the electrons you need. Carbon can form single bonds, it can form double bonds, or it can form a single solitary triple bond. Remember, every bond is a pair of shared electrons. So I can make 4 of those, 2 of these, or 1 of those. Because that would actually be 6 electrons, right? Let's see how the carbon can make some of these bonds. So here we have carbon bound to its hydrogens. This is organic, and that carbon has 1, 2, 3, 4 single bonds. But this carbon also has 4 single bonds, 1, 2, 3, 4. count how many electrons are around that carbon. If each pair is represented by a single dashed line, I've got 2 here, 4, 6, 8. Happy carbon. This is shared between these two, so they're still sharing those electrons. So this carbon is containing 2, 4, 6, 8. Happy carbon. How many electrons for the hydrogen? 2. It's happy. Everybody's happy. All right, go over here and we can see the double bond. Right? This carbon has 2, 4, 6, 8. So nothing can go down here. It will be overloaded. There's no room for it. Down here, this carbon has 2, 4, 6, 8. That carbon has 2, 4, 6, 8. Everybody's got 8. Right? Whether you use single bonds or you use double bonds, there's no example of a triple bond here. But if you look at a compound and it has nothing. Now, how do we make these things? Well, we have some definitions and some vocabulary. What's important to understand in biology is how compounds react within water. Because you are mainly water. To describe that, there are 2 words you guys need to memorize and understand. One is the term called hydrophobic, and one is called hydrophilic. I will press upon you the ability to look at a word and break it down. What does the word mean to remind you of what its function is? What does hydro refer to? Does anybody know? Water, okay. What about phobic? Fear, right? Hopefully you guys will become phobic of John as the quarter progresses. Right? What does philic mean? Like philos, Greek word for love or like. So you've got water liking, but water fearing, right? That's the literal. But I want you guys to give me the biological, not the literal. The literal is to help remind you of the actual biology. Any substance that does not dissolve easily or is not transported easily. Any substance that does not dissolve easily or transported easily in, what do you think? In water. All right. Let's get, anybody have an example of something they know that just does not mix very well with water?
Oil.
Oil, exactly, right? So yesterday I made, and blank